All right. So let's take a deep breath and try to focus here. I need like an hour. You know, if you guys can focus in for an hour, we can be done in an hour pretty easily. If we kind of get scattered off track, like it may, that may drag a little bit more, but we'll be okay. So chapter 11 we're going to be talking about is our last calculus set of topics. And what we're going to be doing this time is talking about going backwards from the derivative. So, like last chapter, if we had something like 3x squared minus 4x plus 5, and we did our derivative. What's the derivative of 3x squared minus 4x plus 5? Great. So if we go backwards from that, that's like the anti-derivative is what we're talking about. So we'd say that 3x squared minus 4x plus 5 is the antiderivative of 6x minus 4. Everybody's okay with that idea? Okay. So let's figure out how we go and do that backwards in general. So recall, to take a derivative, we had this rule, right? Okay. So let's kind of imagine what we're going to have to go backwards. Okay, so we need to cook up a symbol here for the antiderivative. So we're going to use this set of symbols to represent that. This is called the integral symbol. All right, so let's look at what we have to do to 6x to turn it into 3x squared. So what do we have to do to the coefficient? To go from 6 to 3. Divide by 2. What do we have to go from x to the first to x to the second? Add 1 to the exponent, right? That new exponent is 2, which is what we divided by. So it looks to me like the anti-differentiation rule is going to be adding 1 to the exponent and then dividing by that new exponent. And that rule works for us as long as n isn't negative 1. Because I'm telling you why it doesn't work for that one. Because you're looking at it like the n is 1 in this case, right? The n is 0 in that case. Does that, you feel okay? Here's a crazy thing. Like, is there an antiderivative when n is negative 1? Sure. Anybody other than Maria want to take a guess as to what that antiderivative would be? Maria knows already. The antiderivative of x to the negative 1. Just take a guess. You'll never guess. No. No. No.
1.
No. Not infinity.
There is nothing. There's no answer.
There is. It's a function.
You take a guess.
Undefined.
No.
I already said that. It's a fraction.
No.
It's a negative.
No.
It doesn't
The
be true.
antiderivative of x to the negative 1.
Yeah.
All real numbers.
It's the natural log of the absolute value of x.
No.
Right? Now,
What's going on? I thought we were moving.
now, do you guys need to know that? No. I'm just telling you that there is one value for n in which this formula doesn't work. I'm just mentioning what you would use in that case that is beyond the scope of what the IB people expect you to know for this class. But like Maria knows this, Tori should know that if she's taking her calculus class online. She's making a face like I really did not know that.
I know all.
Okay. Yeah, here you go. I have no idea. I didn't draw it.
Is he just saying
I didn't draw it. I can't speak to what the f of x cat.
it's not cute yet?
I think Nick Martelli was involved in the drawings. Yeah.
It's so cute.
Okay. Everybody's okay so far? We have a small problem though, because what if I have f of x equal to this? What's the derivative of 3x squared minus 4x plus 2 going to be? 6x minus 4. But the antiderivative of 6x minus 4 dx we said before was 3x squared minus 4x plus 5. And now you're telling me that the antiderivative of it should also be 3x squared minus 4x plus 2. Same input, two different outputs. That's bad. That's bad, right? We don't want that.
Do you need help? Do you want some M&Ms?
No, thank you. I'll hold out for Cheetos.
I got pizza if you want.
Oh, wait, buddy. I have mine today.
I knew you would. All right. So, thank you. I appreciate that. So what's going on here? What's going on?
So we gotta.
Because this is a problem, right? We should not have two different outputs, right? So, well, remember what's happening to this number at the end when we take the derivative of it. What's it turning into? 0. And that number is now unrecoverable from our antiderivative because we have no clue just by looking at f prime what that constant at the end was. So instead of writing a number at the end, we're just going to write plus c to acknowledge that there is some number at the end. We don't have enough information to say what it is. Okay? So we would say then that the antiderivative of 6x minus 4 is just 3x squared minus 4x plus c. And that's the answer that we're going to give. That's it. So we're going to call that guy like the general antiderivative because we're acknowledging that there's like infinitely many possible answers there because you could have plus 1 at the end or plus 2 or plus 3 or plus 7/8 or negative 15 or whatever, right? Infinitely many answers, but it's going to be like that stuff and then plus some constant at the end. Everybody feel good so far? All right. So far, so good. Let's practice now computing some of these antiderivatives. Sound good? Oh, well, before we do that, one other property here, or properties. So you know how when we do the derivative of something, we can do like, we can pull the constant out front, and then we can just like do the derivative of each chunk, right? Like we do this all the time. Like even without even thinking about it? Everybody's okay? Like you guys recognize that we do that all the time? If we were to do the antiderivative or do the integral of this same thing, guess what? We can use all those same properties. Where we can distribute that integral symbol. We can pull constants out front of it. Everybody's okay? Just to be clear as to like what you can do. So it works the same thing, the same way as that derivative operation where you can distribute it across, you know, the terms of a polynomial and pull coefficients out front and just kind of ignore them and tack them on at the end. All right, so let's do some examples. I'll start off doing the problems, and eventually I'm going to ask for some of you guys to help yell out some answers here on how to do stuff once you're feeling a little bit braver. I know that in the beginning it's really scary. So I'll start. So we're going to do the integral of 4t dt. So I'm going to use my rule for antiderivatives. So I'm going to add 1 to the exponent and then divide by the new exponent. It's going to give me 4t squared over 2. If I reduce that down, that's just going to be 2t squared, and I'll tack on my plus c at the end, and there's my answer. Not too bad, right? Let's do another. I'll do c. So here's the antiderivative of 14. So that's really 14t to the 0, right? Yeah. So I have 14 to t to the 0 plus 1 over 0 plus 1, or just 14t, and then I have to tack my plus c on at the end. Everybody feel good still? Yep. Let's do I guess. Get it? I guess. Okay. So there's one little problem with the way this problem is written, is I can't do this problem with the x in the denominator here, right? My anti-differentiation rule doesn't work unless it's like a times x. This is a over x. What is the cheat that I use to fix that so I can do it? Yeah, I'll think about it just as 5x to the negative 2. Exactly right. So I'll have 5x to the negative 2 plus 1 over negative 2 plus 1, then plus 3x to the 1 plus 1 over 1 plus 1. So that's going to give me negative 5x to the negative 1 plus 3x squared over 2 plus c. And if I wanted to, like, I could write that as like negative 5 over x, which is fine. Or I can leave it like this unless the directions specify that it, you know, like that it doesn't want negative exponents or something. Like either answer is okay. What do you guys think so far? So far, so good? All right, who's feeling brave and wants to try doing h for us?
I gotta see h.
What?
Just start talking it through with me. I'll to let you know if you get them wrong. Be a risk taker, you know? Take a risk. You got it.
No idea.
So far, so good.
plus 1 over negative 2 plus 1 plus
It's okay. Everybody feel so far so good? So if we clean this up here a little bit, those simplify down like that, and we just tack a plus C on, and we're done. How'd they go?
I didn't eat them all.
Oh, why not?
I don't want them all.
Oh,
Did you want some?
no, thank you. I just didn't know if, like,
I haven't opened my
you found,
Cheetos
like, a
yet.
worm in them or something.
No, that's kind of gross, so I don't want to eat my Cheetos.
Okay.
Well, if you want this Cheetos.
I mean, I kind of want those Cheetos, but that's what...
Oh, you're actually giving it. I don't want that.
Yes. Thank you. All right. How do you guys feel on just doing this antiderivative process?
Do I get extra credit for giving that?
Just in my heart, like extra heart credit. How's that?
That works. Yeah.
Is this feel manageable? Fairly easy, right? Not too bad. Basically the same idea. Now, what if we want to find that C? Well, to be able to figure out what the specific C is, no, it's not. It's no big deal. You just need another piece of information. You need to know any point on the original function. So if I knew any point on the original function, I would be able to find the specific C. Without that extra point, I can't do anything to find the C. So for example, if I ask to find the antiderivative and I'm given an extra piece, that's what their textbook refers to as a boundary condition. I can use that extra piece now to find the specific C. So let's do A together here. So the antiderivative of f prime would just be the integral of f prime, which is the integral of 50x plus 25 dx, which is 50x squared over 2 plus 25x plus c. Or just reduces down to 25x squared plus 25x plus c. Everybody okay so far? Now I'm going to use that c. Since I know that f of x is equal to 25x squared plus 25x plus c, and I know that f of 1 is equal to 6, I know that 25 times 1 squared plus 25 times 1 plus c has to equal 6. Oh, 6d, excuse me. Everybody feel good? Now all I have to do is solve for 60. I subtract 50 from both sides and I get c is 10. Oh my gosh, this is like so much more complicated. It's no big deal, guys.
Oh my goodness.
It just,
Fractions in it?
no, there isn't even a fraction. What do you guys think on that? Pretty manageable, right? It's the same idea as the previous problem. You just had one extra step at the end where you plug in an x and y and find the c. Oh no! It's like finding the y or the b value in, like you would have in Algebra 1, right? Except your function might not be linear, but like, whoop-de-doo-doo. What do you guys think? Do you need to see another example of doing this, or is that pretty straightforward? Yeah, I thought so too. I thought so too. All right. I think the worst. I think the worst thing you guys will see in this first section are going to be like the story problems, and I'm just gonna. Yep, I'm just gonna get on my soapbox here and say that, like, once again, I hate the people that edited this textbook because they consistently have like preamble to problem on one page and like all the parts on the other, where it's like, this is the most, like, just have a hard break and put it all on one page so I don't have to flip back and forth and back and forth and back and forth looking for information from the preamble to use to do the parts. Like, just drives me nuts. And they do this all the time, all over the place. It's like, look, the 12 pages that you saved, I get. You saved like 3.7 cents for every book that you printed by doing this. But like, you could have just like rearranged some stuffs probably and got it to fit. You know, just take off the stupid full page cover for each new chapter. You know, like you burn a whole page with some giant graphic at the start of each chapter. Just get rid of those. You save more pages doing that. Anyway, all right, let's read this. So it says a factory has modeled the marginal cost of producing sunglasses as C prime of n equals 45n squared minus 130n plus 80, where C prime of n represents the additional cost in US dollars for an additional pair of sunglasses, and n is the current production level in thousands of sunglasses per month. The factory is currently producing 1,000 pairs of sunglasses per month at a cost of $50,000 US dollars. Write down the units for the antiderivative function C of n. Okay, so let's talk about some stuff about the integral in general. So if I'm doing the integral of some rate function, the integral is going to act like an accumulator, and it's just going to give you the output's going to be a total. And we do this all the time, right? Say you're driving your car at 50 miles per hour over the course of 10 hours, right? How far did you go from hours 3 to 4? Well, 1 hour at 50 miles per hour, you accumulated 50 miles total of distance, right?
I thought you should be.
Yeah,
You are late.
it's fine. I was asking, and then you were like, usually I give you like 2 or 3 minutes to get here because that's just how Sam rolls. And then still not here, and everyone's like, he's here, I saw him. I'm like, well, he's not here now. Yeah. All right. Now, let's talk about this units situation. So remember we talked about in chapter 9, position, velocity, and acceleration, right? Yeah, this is like, let's try to focus in on this idea, because this is not a difficult idea, but like subtle. So remember when we talked about in chapter 9, position, velocity, and acceleration were all derivatives of each other, right? The units for position would have been meters, velocity meters per second, acceleration meters per second per second. That means that if I'm going and doing the antiderivative, if I was in meters per second, I go to meters per second. I lose one of those pers. If I go from meters per second and I anti-differentiate, I'm going to end up in meters. Everybody's okay with that idea? So for this problem, we have C sub n and we have C prime of n. If I know the units for C prime of n, I can find out the units for C of n really easily. So let's read what C of n says again, or C prime of n says again. Yes. Yes. It says C prime of n represents the cost in US dollars for an additional pair of sunglasses. So the unit for C prime of n should be dollars per pair of glasses. Everybody agree with that? We just read that out of there. So what should the unit for C of n be after we do the antiderivative of C prime of n? Just dollars. Does everybody feel okay with how we came up with that? So again, if I take a rate and I integrate that rate, I accumulate whatever the numerator of that rate is. So just keep in mind, if you have like a complex rate, like the numerator of acceleration is meters per second. So that's like the numerator, so you accumulate that. Here, the numerator is meters, so you accumulate that. Does everybody feel okay? It's going backwards from the derivative. Oh, conceptually what we're doing, we haven't talked about conceptually what this is. We'll get to that in the future chapter. Right now all we're doing is like trying to go backwards from a derivative symbolically. We haven't talked about like what this actually means in principle yet. This is how our textbook presents it, which I think is backwards, but that's what we're doing. Is everybody okay? All right. So for part A, we have that. It's just dollars. Everybody feel good? It then says, find the function C of n for the cost in thousands of US dollars for producing n thousand sunglasses per month. So that's just going to be asking for the antiderivative of C prime of n. Well, that's easy because C prime of n is just the function 45n squared minus 130n plus 80. So when I do the antiderivative, can I just do that quickly in my head? You guys seen enough of like me plugging in the formulas? Yes. Yes. 80n. Well, I'm not going to use a C here because I already have a C there. I'll just use D. Whatever. Maybe you want to use K for constant, like you're a German or something. Oh. Okay. So that's our answer for B. Great. Oh, nope, that's not our answer for B. We need to figure out D now. How am I going to solve for D? Well, it does tell us the factory is currently producing 1,000 pairs of sunglasses per month at a cost of 50,000 US dollars. So that sounds like a point to me, but I have to be a little careful because they're being really rude with our units, because we told us that N is the production level in thousands of sunglasses. So 1,000 glasses really means that N is equal to 1. And in part B it says, I want C of N in the cost, in thousands of US dollars. So $50,000 really means C of n, well, I should say C of 1, should just be 50. Rude, but fine, okay. So all I'm going to do is drop the 50 in for C of n, and then a 1 in for n, and solve for, in this case, D. So let's see, we have 90 minus 65, which is 20. 95 minus 65, which is 30. When I subtract it over, I get 20 for D. Whoa, nice push. There we go. Everybody feel good there? Now part C says, find, sure, Isaac. Ms. Lytle needs to speak with you for a moment.
Thank you.
Sure thing. Come on, man. Part C says, find the minimum total production cost and corresponding production level. What does that sound like to you guys? Yes. That sounds like a question from last chapter, right? So if I want to find a minimum, I need to look at where the derivative is equal to 0. Everybody feel okay there? Okay. My derivative was 45n squared minus 130n plus 80. That's a quadratic equation. So to solve that, I'll either use the quadratic formula. Since the leading coefficient isn't 1, I want no part of factoring this thing, especially with the size of those coefficients. Yuckarooski. I'll just use the quadratic formula. But I also noticed that each of these coefficients is divisible by 5. So I'm going to do that first just to make the arithmetic a little bit more manageable. 26, and then, yep. This part gives me like, what's that? It's like 676 minus 576, so that's 100. So the square root of 100 is just 10. Oops. I don't know why I wrote 18 twice. That's a 26. So 26 plus 10 is 36 over 18, which is 2. And then 26 minus 10 is 16 over 18, which is 8/9. So I can either do a first or second derivative test to figure out which one is which. I'm going to choose to do a second derivative test because I think it'll be a little bit simpler in this case. So the second derivative is just going to be 90n minus 130. Everybody's okay with that? Just took the derivative of this thing. So the second derivative evaluated at 2 is bigger than 0. So that tells me that x, or actually n is our variable, n equals 2 is a minimum. And if I take the second derivative evaluated at 8/9, again, I don't really care what the number is. That's going to be less than 0, though. So that tells me that that one is a maximum. So there we go. Everybody feels okay there? So Now I need to find that minimum cost, so I'll do C of 2. So then I'll just plug 2 into our thingy-majigger from before. Right? Yeah. And when I do that, I get, I'm just going to look it up, 40. So we'd say when 2,000 sunglasses are produced, total costs are at a minimum of 40,000 simoleons there. Right? Why is it 2,000? N equals 2. Why is it 40,000? Because C of N was, or I should say C of 2 was 40. And each of those was measured in thousands of their respective unit. Does that feel okay? You could have also done a first derivative test and drawn like the sign diagram and used the first derivative. That would be fine also. I just chose to do a second derivative test because it felt easier computationally to plug that stuff into a linear than it felt to plug it into a quadratic. Since I didn't factor it, if I had factored it, I probably would have done a first derivative test, but I didn't. I used the quadratic formula because it looked like it was going to be a pain in the neck to factor. What kind of bug is it? Okay, you are much bigger than it though, right? I don't even think it has teeth. I think you just live and let live there. I don't think that bug wants anything to do with you.
Not with my shoe.
No, I don't want to kill this thing.
Oh, yes. How do you open the window?
It doesn't open. It has a screen in it. Yup. Go help yourself. All right. So in 11.2, we're going to talk about the definite integral. So here's the idea. Now we're going to introduce so this guy is a definite integral. What we did before this guy is the indefinite integral. Or the general antiderivative. You could use those two terms interchangeably. Sit somewhere else if it's going to be this big of a problem. Like I don't know what to tell you. You know, it's just a little bug. I don't know what to tell you. Is everybody okay with the vocabulary? Yes. We call the A and the B the bounds of integration. The one on top we would surprisingly call the upper bound. The one on the bottom we'll surprisingly call the lower bound. I know that's shocking to everyone involved. Yeah. So let's look at how we do this in practice.
So the derivative will be indefinite and
When there's bounds on the integral, that's a definite integral. When there are no bounds, that's an indefinite integral. The difference is the definite integral is just going to be a number. The indefinite integral is going to be a function. I think it's like once you start doing it, it's that part's like relatively obvious, but this is the first time seeing it. So like I'm just trying to be clear and like talk through it. All right. So let's do a couple of these. Everybody's okay? So I'm going to first start by doing the antiderivative of 3x squared, but it gets no c. What's the antiderivative of 3x squared? X cubed. Nope, just x cubed. And then we're going to evaluate that at 2 and 0 and look at the difference. So the answer here is 8. So it's just like doing the other problem, and then you just plug in some number at the end, or numbers. Let's do this one. Okay. What's the antiderivative of x cubed? So you add 1 to the exponent and divide by the new exponent. I know. That's why I said it aloud, because I see you trying and you're just like, I'm not seeing the pattern. What is it? And you asked Henry like 4 times and he apparently just is going to ignore that question. So even though he can do it effectively.
I was making a note.
It's okay. Everybody's good so far? Now we're just going to plug 1 in and plug negative 1 in and subtract them. It's always the upper minus the lower. Whoa. This is just crazy, Mr. Kulik. What do you guys think? You feel pretty good about doing this process? Can I show you something awesome? Watch this. So if I go to our calculator, guess what the calculator can do? Definite integrals. So to do that, I'm going to press the math button, and I'm going to scroll down to, on my calculator, it's command 9, called fnint. And now I can just type in the problem like it looks like on my sheet of paper. So if I wanted to check that first one that we did, I can just type it in exactly like it looks on my sheet of paper. Press enter. Everybody feel okay using that? So the calculator can do all these indefinite integrals. Guess what it can't do though? Can't give you the equation for the definite integral, but guess what it can give you? It can give you the graph. So, for example, if I wanted to graph, say, 3x squared, and check to make sure x cubed is the same antiderivative, I can go to the y equals, and I'm going to type in math, and I'm going to pick fn int. I'm going to do 0 to x. I'm always just going to do 0 at the lower bound and x at the upper. 3x squared dx. And then I thought the antiderivative of that should be x cubed, right? Everybody okay with this? So I'm going to change the way this graphs so it's a little bit easier for us to see. So I'm going to have the integral, what the calculator says the answer, it's going to draw it in for me, but it's going to have that little circle where the pencil is, so it's easy to see it kind of be traced in. And then this one, the answer that I provided, that we're checking, I'm going to have the calculator it's just going to trace it, but it's not going to write anything. It's just going to move along the path. And I'm just going to graph that on a standard window. So I'm going to do like a zoom standard. So here comes the graph of the integral. The calculator's computing it right now. What you're going to find is that this takes a long time for the calculator because of the methods that it has to use to do this are not easy, but this is the calculator drawing in the integral, the antiderivative that it's calculating itself. That's its graph. And in a second, you're going to see the calculator trace in our answer for the antiderivative. And if the two graphs match, what should that tell us? We did it correct. And see it trace in the other one. It followed the exact same path. I must have done it correctly. Isn't that wonderful? Super nice. Thank you, calculator. What a kind friend you've been to me all these years. I really appreciate you. Calculators are evil. You know what's going to happen on the next test there, Jack? Yours is going to fail somehow. It's going to be like, I'm out of batteries. Oh, my operating system's going to crash.
That'd be fine.
It's like, I don't need you anyway.
I should probably.
All right. I have one more example problem to do. And we'll call it quits for today. How's that sound? All right. Yes, it is. A tank containing 10 cubic meters of water is draining. The change in water volume is given by dV dt equals yada, 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 where t is in minutes since the tank has started draining. Find the change in volume of water in the tank in the first 3 minutes. So it's asking for something as volume. So to find that volume, we're going to do the integral of the rate from what to what? 0 to 3 is correct because it's the first 3 minutes. Time would start at 0 and end at 3. Guess how I'm going to do this? On my calculator. That's the work that I'm going to write down, unless it tells me specifically I need to show more work than this. I'm just going to do that and then type it into my calculator. The only difference is here I'm going to use x's instead of t's because the calculator is confused. If you start changing variable names, just use x the whole time. So I get negative 1.4991. If I round that to 3 sig figs, I'm going to get negative 1.50 cubic meters. So I'd say the tank has lost 1.5 cubic meters in the first 3 minutes. Everybody feels pretty good on how I did that. Next thing it says is to find the amount of water that drains in the time between 4 and 8 minutes since the tank has started draining. What am I going to do to compute that? Oops, I should have a dt at the end of that too. Okay, so we'll just go do the same thing on our calculator. Guess how I'm going to do that? I'm going to press second and enter. That retypes the whole thing I just had, and I'll just go back and edit the bounds. That saves me a bunch of button pushing. So that gives me, rounded to 3 sig figs, 2.00 cubic meters. So again, I'd say, you could give the exact answer, but I'm just going to round them to 3 sig figs. Sure. Yeah. Yeah, we could do that. All right. Part C says, find the time at which the tank will be empty. Yep. It said there was 10 cubic meters in it to start. Yes, it does. So you can do two things. You can either see when this I should make that x is equal to negative 10, or if I add 10 to both sides, solve when that's equal to 0. It's doing the same thing. I'm going to do this way because it's easier to do on my calculator, because I know a better idea of what my window has to look like, because I know I'm just going to be looking for the x-intercept as opposed to an intersection between the two curves. So I'll set this up on my calculator. I'll do 10 plus, and then we'll do the integral from 0 to x of, what was that? 0.0002x minus 0.5 dx. I'll clear that out. And now I'm going to pick my window here. Remember, this x is going to be a time, so the x min should probably be 0. From 0 to 3, I lost a cubic meter and a half. Between 4 and 8, I lost another 2 cubic meters. I only have 10 total. I'm going to guess like 25. It should be empty well by then. Yeah. So I just want to make sure I can see the x-intercept. So 25 seems more than sufficient to get that thing emptied. So now I'll hit graph. And here comes the picture coming in. Yep. And again, the worst part about graphing the integrals on your calculators is just that it's a little slow. But no big deal. Like, I can start a problem like this and then just start doing something for the next problem. I wait for the calculator to graph it if I need to. And there's my intersection, but unfortunately, before I can go and find the 0, I got to wait for it to finish graphing. So if this was me, I'd just like move on to the next problem for a little bit and come back. Be like, okay, now I got what I need. So second calc. I'm just going to do the 0 command. So that looks like a good left bound. And I'll move my cursor over until I'm on the other side of the x-intercept. There we go. That looks good. Press enter and enter.
As you get a good total of
20.1 minutes. Oops. So we'd say x is about 20.1 minutes. And again, my work is just writing the equation and then doing it on my calculator, which is sufficient. They will credit you for work on that on the IB exam, because you are allowed to have your calculator the entire time. Calculator methods are valid methods unless they say, like, show. You don't have to do you don't have to show them much It just, like if it just says find, like this question just says what, like how long does it take for it to drain? I'm just going to set up the equation I solve for, solve it on my calculator, write down my answer. Oh, sure. Yeah, you could model it. All right. Guess what? That's it. Look at the time, too. 55 minutes. Was I bang on there? Well, I was 5 minutes early, which I don't think you should. I mean, I can talk for 5 more minutes. I mean, I got plenty to say. Oh, you mean we can talk about the fundamental theorem of calculus and state that and talk about the derivation of these things, but only to you and everyone else in the room, aside from me. All right. No, this has been fine, right?
Calculus is just a weird algebra.
Yeah. All right. Worth noting here, this problem set for 11.2 is due when?
Sunday.
Next Sunday, because
You actually like us.
well, we had the test on Tuesday. We don't have a chance to ask questions. We had the test on past tense.